All right, this is
University. So Heng-Tong got his PhD in Bielefeld in Germany in 2010, and then worked at Brookhaven National Lab and Columbia University as a postdoc, and then joined CCNU in 2013. And he's currently vice director of the key laboratory of quark and lepton physics on the Ministry of Education. I've known Heng-Tong for quite a long time, since our interests overlap quite a bit. And so spectral functions is a topic of great interest for me for a long time. And so I'm happy that he's here to give a talk. Thanks.
Yeah, good. Thanks a lot for your invitation, also introduction. Yeah, I do look good for a long time, since my PhD days. So I started working on this aspect functions since my PhD in Bielefeld University, and that time I was mainly focused on the MEM, maximum entropy method. Now we're trying to reconstruct aspect functions using a totally different approach, that is machine learning techniques. So that is the topic of today, what I'm going to present to you. So this work is done together with my student Siyang Fei and the collaborator Gabo and Chunbing Yang. So most of hands-on work has been done by the students, Siyang and Fei Liu. So in this talk, I'm first going to give a general introduction on the aspect function and why the aspect function is so important in Lattice QCD, and then I'll tell you something about the traditional method, that is the maximum entropy method, and then I'll propose a newly neural network, that is the sVAE as variational auto-encoder, and then I'll make some mock data test, and finally give an application to a real Lattice QCD data in the charmonium sector. Okay, so Lattice QCD as a first principle of the initial method has been very successful to compute, for instance, the Hadron spectrum. So once the up quark mass, down quark mass, and string quark mass is fixed, one can compute the whole spectrum of hadrons. For instance, one can get rho meson mass and eta meson mass, and etc. And it has been very successful. So this is the case in the vacuum. One can certainly extend the case to a non-zero temperature, just hit a vacuum. So for instance, when you look into the left-hand side plot, this shows a QCD equation of state. So you can see here that the pressure as a function of temperature, it just increases, and it's the same situation for entropy density. And you can see from this plot, there's no singularity. So this suggests that the transition from hadronic phase to quark-gluon plasma phase is just a rapid crossover. And this rapid crossover temperature has been determined very recently. Okay, someone has questions or it just echoes? Okay, so this transition temperature has been determined very recently in a very precise number, just in a continuum limit. And its transition temperature is about 156.5 MeV, and this corresponds to a unit that everyone is familiar with, is 1.8 times 10 to the power 12 K. And we know that room temperature is about 300 K, and the temperature of solar center is about order of 10 to 7 K. So its temperature for the transition of QCD is 5 orders higher than the temperature in the center of the sun. So since the transition is not a real true transition, by true phase transition, I meant that there's no singularity in this transition. It's not a first order or a second order, it's just rapid crossover. So in this situation, there's no, it's not really meaningful to talk about the carrier phase transition and the deconfinement phase transition, but you can talk about carrier aspect and deconfinement aspect of this transition. So for instance, when you look into the carrier aspect of crossover, you can look into the degeneracy of net hadrons. For instance, when you look into rho meson and A1 meson, rho is a vector, A1 is an X vector. If they are degenerate, you can consider the X1s, and this will signal a restoration of carrier symmetry. So this plot shows the screening masses of various net hadrons in different channels. So for instance, this red and yellow points correspond to the X vector and vector. You can see clearly that in this transition temperature range, denoted by this gray band here. You can see the degeneracy of rho and A1. So this certainly signals restoration of carrier symmetry already in the range of carrier crossover transition temperature. This is for screening masses. And the right-hand side, well, you can also have a look at the confinement aspect by looking into heavy hadrons, for instance, quarkonia. Since quarkonia is very heavy and its size very small, so the quarkonia can survive deep in the confinement phase, and it can be considered as a QCD, QGP thermometer. So this plot is showing that a ratio of screening masses in the pseudo-scalar channel are divided by the eta B mass in the vacuum as a function of temperature. You can see that at temperature around 400 MeV, so this is about 400 or 500 MeV, you can see this ratio is about just at most divisible by 5%. And this 500 MeV is close to 3 TC. So this just means that the eta B still survive in the confinement phase transition, the confinement phase. So what I talked about before is just for screening masses. The screening masses actually is not really a pole mass. The screening mass is only equal to a pole mass in the vacuum. The more information actually are encoded in the Hadron Spectral functions. So for instance, this shows a schematic plot of Hadron Spectral functions. So x-axis is omega, this is energy, and y-axis is the spectral function divided by omega. So at very low temperature, the spectrum of hadron in a certain channel can be represented by this delta function. And this is the ground state and this Hell excited state. And then comes with a continuum part, which represents a continuous states of hadrons. And if you increase the TC, TC close to temperature, close to transition temperature, that is represented by this red line, and this delta function will be smeared into some Bragg-Wickler peak. And for high excited states, this peak will be smeared more into much wider peak, and also this continuum probably will move to a lower omega range. And if you increase the temperature again, so even the ground state peak will be deformed very much, and as you can only see a bump here, very low bump here. And if you go to a very high temperature, that's infinite temperature, probably there's no peak structure anymore. There's only exists a continuum spectrum here. So by looking at this deformation of spectral functions, you can get the idea that when and at which temperature this quarkonia states or hadron states will be dissociated and or melted. On the other hand side, when you look into spectral function, the slope of spectral function at omega equal to 0, you can also get the idea of a diffusion of charge or quarks. For instance, you can get heavy quark diffusion coefficient from the vector quarkonia correlators, and this corresponds to heavy quark diffusion coefficient. And this heavy quark diffusion coefficient is very important because it can be used to describe the propagation of heavy quark in the medium when it transfers in the QGP phase. And this whole process can be described by the Lagrange equation, and this heavy quark diffusion coefficient is very important input in this model. This is not only saying that Hadron Spectral function can tell us there are more. For instance, if you compute the spectral functions in vector channel that is related to the electromagnetic current operator, you can also get, for instance, a photon emission rate or emission rate of the lepton that from a virtual photon. I will not really go into these formulas here, but I just want to tell you that the Hadron Spectral function is a really important quantity, and I really want to study this quantity. But the problem is that we cannot compute the Hadron Spectral functions directly on lattice. What you can directly compute on lattice is just temporal correlation functions. And the temporal correlation functions can be expressed can be computed in this way. This is just some average of product of two bilinear forms. And this JH have the form of like this. This gamma H here is just some certain gamma matrices corresponding to different channels. So for instance, if this gamma H is gamma 5, so this corresponds to a pseudo-scalar channel. In the quarkonia case, this corresponds to an ELC particle. And on the other hand side, the spectral function is defined as an imaginary part of the target correlator. So by doing the unlinear continuation, this correlation function in the Euclidean space can be related to this dynamic quantity that is a spectral function. So in general, we have the spectral representation summarized in this equation. So left-hand side is Euclidean correlation function is computed on a lattice. And right-hand side is a spectrum in real time multiplied by the kernel. So this is a Koch kernel here. And this kernel, you can observe here, there is a temperature dependence of this kernel. So as before I showed you in the schematic plot, we want to look into the temperature dependence of the spectral function. And unfortunately that this kernel also have a trivial temperature dependence. So this makes things very complicated. Let's have a look into this problem more in detail. So to get a spectral function from the Euclidean correlation functions, so actually this is very difficult because this is a typical yield-post inverse problem. Since we can only compute the temporal correlation functions at the discretized data points, that is at the order of 10. And however, at the end of the day, when you want to have a spectral function continuous and has a order of 1000 in the omega space. So this is a typical inverse problem. And in principle, there are infinite number of solutions exist. So if you don't know the answers, so this is gonna be a disaster. And the real case is that we don't know the answers. So this is really a disaster. That's what we call the yield-post inverse problem. So there are many different methods trying to solve this problem from last 70s, from last century, from this Beck-Gilbert method and Tikhonov regularization method. So these two methods have also been used recently if there are not so many data points in the temporal direction, especially in the case of QCD simulations. There are also methods as a maximum entry method that has been introduced to Lattice QCD by Asakawa, etc. in 2001. There's also there's an extended maximum entry method with a different entropy term proposed. There are also the stochastic optimization method, basically the extended version of MEM. So since in my talk that the machine learning method is basically inspired by the maximum entry method, so I'm going to spend some time to explain this maximum entry method. So this maximum entry method, it basically is to extract spectral function without any ansatz for the spectral function. It has been successful in quantum matter physics, astrophysics, and etc. So basically, it's a method to obtain the most probable image from insufficient data because there are infinite number of solutions exist. So from this method, one can get the most probable image. The beautiful thing is that if there exists a maximum value of this entropy, so they're gonna exist a unique solution. This MEM basically is based on the Bayesian theorem. So basically that for this probability that is given, the probability of X given Y is equal to the probability of Y given X times the probability of X and divided by probability of Y. So in this situation, we can use this one to transform the probability of a spectral function given the correlated data G and prime information H into two different terms. Because at the end of the day, we need to maximize this probability because we want to get the most probable image of a spectral function. So we can transform this guy into these two terms. So this blue term is nothing but just the likelihood function. It's proportional to likelihood function because this is a probability of G given rho and the prime information H. This is quite normal because we have people has used this likelihood function to do a standard chi-square fit. An interesting thing is about this prior probability. That is probability of rho given prime information H. So this one is proportional to exponential of alpha times S. So this S here is information entropy. It can be expressed in these terms. Basically, this is a Young-Yenes entropy term. So there's a term that is called m omega here. Actually, this is called deformable. And the deformable includes basically the prior information on the spectral function itself. For instance, if for Hadron spectral functions, this rho is positive definite. And this m omega is very important because this is only input parameters in the MEM analysis. So when you do MEM analysis, you certainly want to check the dependence of the output spectral functions on this parameter, on this deformable. So if there are some structure which are independent of this deformable, so this structure I consider to be stable. Otherwise, if your structure depends a lot on the default model, that means this structure are not stable at all and not reliable. The other interesting parameter is also this alpha. So basically, at the end of the day, we want to maximize this alpha S minus chi-square divided by 2. So this alpha here basically controls the relative weight between likelihood and entropy, because likelihood tends to fit the spectrum close to Collet data. However, entropy term tends to fit the spectrum close to deformable. So here shows an example of deformable dependence of MEM analysis, which we have done a very long time ago. This plot shows the result for Untitled 96 for vector spectral functions at 0.73 TC. We can just focus on this panel here. So these dashed lines means different deformables with different colors, different deformables. And these solid lines are outputs from MEM. You can clearly say that for the spectral function at omega smaller than 5 GeV, this structure is very stable. So this is totally deformable independent. So in this situation, we consider this structure is very robust and it can be reliable. And actually, when we read off from this peak location, actually just corresponds to the Gibbs mass that was tuned on our lattice. However, if you go to higher temperature, since we are using a fixed scale approach, so when you go to higher temperature, that means your number of data points in the tau direction becomes smaller and smaller. So at temperature about 1.5 TC, you will see that this output spectral function depends on the different default models, and the situation becomes much more severe when you go to interval 24. You can see that this output spectral functions basically just follows the trend of the default models. And here, maybe it's not really easy to say. We also have a large default model, which is called the default model 1 here, that is just represented by this black dash line, black dotted line here. You can see here that with interval 24, the MEM output, that is the black solid line, just overlap with this black dotted line. So the deformable dependence is really serious here. With tau is very, very small.
Heng-Tong, all the default models you have shown here on the right, they all have either cut at 2 or 2 GeV. I mean, are they based on the kind of...
Yes.
Why was it done?
Yeah, certainly you can just also study the dependence on this, because we consider just using the free continuum part. So this starts with 2 times quark mass. So you can see here the quark mass is 1 GeV. So it starts with 2.
Okay. But of course, now you can never, in a way, by this choice of default models, you can't get
yes.
in the gap. Yeah. Okay.
Yeah. The point is that here the deformable dependence is very large. You can certainly just lower down the threshold here, probably you will get a different answer. So that just illustrates my point that okay, the deformable dependence is large. Yeah.
Okay.
Okay. So this is what it is, right? So since very recently there's a lot of applications of machine learning techniques in various topics in nuclear physics. So you can see some topics from this very recent review. So in this situation, we're thinking that, okay, why we can just use machine learning to reconstruct spectral functions from Lattice QCD correlated data. We don't really know the answer. Maybe it cannot really beat MEM, or we can just get very bad results compared to MEM, or we can just get some advantage over MEM. So this is something we're gonna try. So actually, we look into references. That actually, there's quite some quite interesting studies has been carried out in reconstructing spectral functions using machine learning. There's all these papers. Certainly, there are more. Sorry, probably I didn't miss some reference here. But however, in most cases, what they used in the loss function is that they use this general neckhood, or just simple difference in the correlator and spectral functions. So in this situation, you don't really include any prior information, because keep in mind that this is a yield-pose problem, right? Yield-pose inverse problem. There are infinite number of solutions exists. So this is one big point. And second big point is that during training, many of them, they are using the same inputs for training, and the wanted outputs have the same form. So for instance, if I want to have one double peak, when I train the neural network, I also train it using 2 double peaks. So just like a chi-square fit. So this is something I don't really like. So in this situation, the goal in our current proposed study is to first design a neural network that can learn to balance the prior and neckhood, just include the entropy term. And secondly, that we want to train the neural network using a general input. So the thing we've found that can be very lateral to attack this problem is the so-called variational auto-encoders. So these variational auto-encoders include 3 parts. So first is a encoder, and then a decoder, and a loss function. So the encoder here, it shows like this. If we have a data X, and then you can encode this information into a Latin space Z. And this Z information, of course, this is a model building here, and this is what's called recognition model or inference model. And this probability QZX here, just the probability of Z given X. And this phi here is just some variational neural network parameters. And once you get the latent variable Z in the latent space capital Z, then you can use a decoder. You can put this latent variable Z in this decoder here to get a data X. And this is called a generative model. So this X is sampled from just probability distribution of P theta given the probability of X given Z. So this is very much like the situation we have in the case of correlator and the spectral functions. So sort of like we encode all information into the correlators, and at the end of the day, we want to decode the correlators into the spectral functions in the omega space. So this plot basically shows the flow of this whole thing. So we have the data set D here, then we enclose the data into the latent space by an encoder. This here is just is latent space, and then we, by using some prior distribution of this latent variable, we can go into a decoder and then go back to X space. That is our data side. So one last piece I want to talk about is a loss function in the variational autoencoder. So what we studied is this marginal probability distribution p to the x here. So we can just, because normally we're looking into a logarithm scale. Sorry, not logarithm scale, just looking into log of p theta. So it can be equal to e, and this eq phi is just expectation value of certain variables or functions according to this distribution. So this here is the exact definition of this expectation here. So for instance, eq zx fx equal to integration of this variable z and with this distribution q and times this fx. So by using the Bayesian theorem, actually this sign here is rigorous. So of course you can notice that the x is our data, right? And the z is a net variable. So this plays a role of encoder. We just encode our information of data into latent space here. So it's encoder here. And then we can go to a second line. So what do we do doing the second line is very simple. Again, we use this Bayesian theorem. We just transform this p x here into the joint probability of x and z divided by the probability, conditional probability of z given x. So this is also exact. And its joint probability of x and z can play the role of this decoder, because you want a decoder means that, okay, your decoder is z into this x, as my mouse saying here. That's straightforward. Then what I can do is that, okay, let's just put a encoder probability both in the numerator and upstairs and downstairs. Okay, and this is exactly the same. And then we can break these two terms, this one term, into two terms in total. So this left-hand side plot looks like this, and right-hand side plot has form like this. So then let me first explain right-hand side plot. This is nothing but KL divergence. So basically that it gives the distance between the model and data distributions. And this KL divergence is always positive definite. So since we want to, at the end of the day, want to maximize this marginal probability distribution of x, and also this guy is always positive definite. So we can call this guy, this term, is the evidence lower bound. So basically, if this guy is fixed, we maximize the evidence lower bound is trying to minimize the KL divergence. So basically, the Q phi here is a model post-prior, but this P theta here is a true post-prior probability, because true post-prior probability is really hard to get, and we can just use this model to approximate the true post-prior. In this situation, if we maximize the evidence lower bound, we can just minimize KL divergence. On the other hand side, in the language of neural network, we also normally talk about loss function. And loss function is just the evidence lower bound with a minus sign in front of it. So whole goal is just to minimize the loss function. Let me just recap everything in this graph. So basically we have data point, then we use encoder, that is an inference model, to encode data x into z, and then sample this net variable according to this Q here. And then we use the z to do some generative process to generate the probability, the probability of the x. Then by using Wallace gradients, we can compute the evidence lower bound for the current VAE, variational autoencoder. And then by putting a minus sign, we can get a loss function. So this is a whole computational flow in the VAE. So if you have understand the VAE, so this is quite straightforward to get our sVAE answered. So in this situation, we propose this sVAE to solve the problem to reconstruct, not to solve, just to explore the reconstruction of spectral functions from collators. So instead of using a marginal probability, so here we're looking to this conditional probability. That is the probability of rho given in the collated data. Yeah, we want to maximize this probability. So again, by using a Bayesian theorem, we can write this guy into this guy. This is rigorous. So you can immediately regularize that. Okay, we introduce a variable z here. This z can be interpreted as a Latin variable. And this guy here, pzg. So this can be interpreted as encoder because we encode the collator into Latin variable z. And again, let's go to the second line. So basically, again, we introduce a Q distribution, a probability Q here. Again, when you look into the form of Q, this gives you the probability of Z given the ground truth value of collator and ground truth value of rho. So again, this Q here can also place the role of encoder. So this is the whole purpose for going from this line to this line. And then using Jensen's inequality, we can write larger than equal sign here from this line to this line. So in this situation, basically this one gives you the evidence null bound. So this is evidence null bound in our proposed neural network. And then we can define the loss function, just put a minus sign in front of evidence null bound. And that is goes through here. And by decomposing this loss function, we can also get two terms. So one is like this. This is with a log p rho zg, and the other term actually is the K divergence term. So we can immediately regularize here, as I mentioned before. So this p here is a probability of z given g. So this actually is encoder because it encodes g into z, and the other one is also encoder. That encodes information of g, gt, rho gt into z. And the other one actually is a decoder because it decodes information from collator and z into this spectral function. So this is a flow from this function. So let's go into more details.
But can I ask a question, Heng-Tong? So
sure.
On the, 2 slides ago, when you introduced the auto-encoder, so one more. So Z was the latent variable, and the data was always X. You go from X to X. Yes. So now, of course, we have rho and G.
Yes.
And so
before it's just marginal, right? It's marginal probability. Now we have conditional probability.
Right.
Yeah.
And you introduced the latent variable Z, like on the first line, but you haven't specified. Well, you don't have to. Do you have to specify what it is, or is it defined in this way, so to speak?
I haven't specified now, but I'll define it as Latent variable later. Yeah. Okay. So basically, you can just consider this as a Latent variable.
Right.
Yeah.
And the way the latent variable appears, that like in the bottom, that defines what you call the decoder and the encoder. Then.
Yes. Exactly. Yes.
Yeah. Okay. Yes.
Right. Yeah. We just introduced sort of like a middle variable, right? It's we just call it a Latent variable in the framework of a variational auto-encoder. Okay, so let's just go to a little bit more details into this loss function. So basically, in this guy, this loss function has two terms. First, not the second term is its K divergence. So basically, this is a Q here actually is a what is called the true probability of Z given the ground truth value of G and rho GT. the difference between this P and Q here, we just want to minimize it, right? Because we want to have this model P as close as to this true value of Q here. For first term, it's more interesting because the first term here actually is also kind of a post-derived probability, but here we can just decompose into 3 terms. So actually, this actually is inspired by MEM. So this term is including these 3 different terms. The first term is prior information because this is a rho given Z, and the second term is a probability of correlator given rho and Z. So basically, this is likelihood, and this guy is just evidence. So for prior information, we can just write it in such formula. This is exactly the same as MEM, but with S has a different definition. The difference is actually here in the variable shaded by a yellow color. So before in the MEM, S here, this is M omega. This is deformable here. Okay, so the deformable you have to choose. When you do an MEM analysis, you have to choose a certain deformable. But in this training process, in sVAE, we know the true deformable, or actually, it's not the correct way we say it. Actually, what I'm saying wrong. In this sVAE, we do know the real spectral function, because when we train it, we certainly know the answer. This is the difference from iterative method. In machine learning techniques, when we train a neural network, we certainly know the true answer in the mock data test and in the training. So this is an advantage of this machine learning over general iterative method. So or we can consider this rho ground truth value of spectral function as the best prior information of a spectral, because this is a true answer. And in the MEM, you have to find out the best prior knowledge of a spectral function. But in the training of a neural network, we already know the answer. So since in our neural network, we have introduced this entropy term S here, so and everything is based on VAE, so we combine these 2 together. We call it sVAE here. That's how the name comes about. Then let's go to the second term, that's likelihood. So likelihood is nothing but just 1 over ZL divided times exponential to minus L. So the form is very similar to the case in the MEM, but likelihood here we define it quite a little bit different way. So if you remember, there's alpha parameter in the MEM, but here we put alpha parameter here downstairs, and again this alpha, it's a little bit similar compared to that in the MEM. This alpha here also controls the relative weight of entropy and likelihood. The same. So entropy term will have rho close to a prior, but the likelihood we're having rho close to a data. And we're going to train this neural network to learn how to balance the likelihood and entropy by this alpha parameter. So this is the whole idea. That's the difference of our sVAE from the previous VAE or conditional VAE. This is a whole key point of our neural network.
Heng-Tong, I didn't understand. So how you choose the value for alpha here?
We don't choose. We didn't choose. It's just generated by the network.
So this is the output from the network.
Yeah, this is the output. Yes, yes.
Yes. I see. Thank you.
Yeah. Thanks for the question. Yeah. I will also demonstrate this later. So this is evidence, but this is just integration of everything. So it's nothing much to talk about. It's very trivial. Then let me recap everything in certain graphs. So here we have the ground truth value of correlator and the ground truth value of a spectral function to be fed into encoder 1. And encoder 1 basically gives you the probability of Z given GGT and rho GT. And then we sample the Z from this distribution and to be fed to a decoder. Then we can compute the rho z and alpha z from the decoder. So this is just answers the question before. So we get this alpha z from a decoder here. By putting this spectrum and pair information, we can certainly get this guy. This is a Q log term that goes to the first term in the loss function. So also here, I emphasize here is P rho ZG is nothing but this decoder. We have two chains of training. This is the first chain in the first row. In the second row, we have a large chain of training, and that is we have this stochastic data G. So basically here is just ground truth values of rho and G. That's one single value. But here, this is some noisy data, stochastic data, just like the data we have in Lattice QCD. So it goes with errors, with many different configurations. And then we fit this G into encoder 2. So from encoder 2, we get probability of Z given G. So this is encoder G into Z space. And then we can use this guy and this guy, the Q and P, to compute the Kerr divergence. So that is the second term in loss function. So by combining this guy and this guy here, we can get loss function. So this is a training flow of sVAE here. Let me go to a little bit details into how we set up in the encoders and decoder. So for encoders, we have basically, for word encoders and decoders, we have two hidden layers, one input layer and one output layer. And for encoder 1, for Q and encoder 2, P, we basically parameterize using this Gaussian mixture model. And with N here, it's just Gaussian distribution. And this mu, sigma, and pi is nothing but just outputs from this encoder 1 and encoder 2. And for rho z and alpha z is also their outputs from decoder. So once a training is done, how are we going to get the outputs, right? So for reconstruction, we just get rid of the first row here. So this is for training, right? We don't need the first row here because when you do a mock data test, when you do a reconstruction, actually you don't really know the GGT and rho GT. Actually, rho GT and DGT are really the solution we want to find out. So we just use this second row to get the results out. So that is what we're going to do here. So we have this stochastic data G to be fed into encoder 2, and then we can sample Z according to its encoded probability as PZG, and then fit this Z into decoder, and then get rho Z and alpha Z. So that job is done. We get rho Z and alpha Z. Okay, let me emphasize here. So in this situation, we don't have any prior here explicitly, but everything is encoded in this decoder here. So this is one of the advantages in our neural network. And then to get the final answer of rho, we first consider because when we minimize the loss function, we do many mini batches in many apples. So here we also consider for certain range of training apples, we get this spec function, and the spec function can be written in the integral of spec function rho z, and then times the likelihood here, and then times the probability of z given correlated data. So in this situation, we can get the spectral within the training apples. And this NC, I've got to mention is number of configurations here. And into a the summation format, and this here NS is a samples of a number of samples in Z. So finally, since that we're not really sure certain training time history, or we can get the true minimum. So in this situation, we consider we just go more, and also some more a certain number of apples in the training to get a mean value. in this formula, and then once average of our training sample is done, we also compute the standard errors from this duration of the training samples. So that is how we get the average value of spectrum and then errors. Okay, so let's move forward to training in our neural network. So what we do what we use in training is a general spec function here. Specifically, it contains two parts. One part is some sum of Gaussian functions. So here this is just a Gaussian function. This MI here is just peak location of a Gaussian peak, and gamma is the width, of course. And this MI and gamma are fixed in a certain range. What we actually sample is the amplitude here, Ci, and also the smeared smeared step function here. For instance, delta 2 and zeta 2 and delta 1 and zeta 1. So basically this Ci and delta 1, delta 2, zeta 1, zeta 2 are sampled randomly. And then we have a second part is the continuum part. So this Ci equals 0 is also sampled randomly and with a smeared step function. So give an idea of a trained spec function too is that, for instance, we have 5 different example training spec functions shown like this. So basically just like random picks plus some continuum here. And the cover range actually is in this gray area. So this training spec function is quite general. That's information I want to give to you. And then in the details, how do I do a training is that first I fit rho GT and GGT into this encoder 1. Okay, so maybe I just faster a bit. And rho GT and GT is obtained from the training spec function. It's called corresponding correlator into encoder 1. And then we fit this G generated stochastically to encoder 2. And how this G is generated? So G is sampled from a Gaussian distribution. And with this GGT, the mean value, and the sigma is its variance. And the sigma is nothing but like this, because we want to mimic the case in Lattice QCD simulations. So making this error actually depends on the tau. And here, actually, this is LT here. So we just use our Lattice QCD data to look into what's the relative error in our Lattice QCD data, and then scale it into the current training process. And then in the third step, just perform the fitting in the step 1 and step 2 simultaneously, and then compute those functions. So for this training, we need to perform step 1, 2, 3 for different n tau. But for each n tau, we just need to perform once. So here comes a mock data test. So left-hand side, we show the input just as a continuum part. It's represented by this black dashed line here. And we show the results of sVAE just represented by this solid right line, and its uncertainty is represented by the purple bond here. You can see here it's more or less reproduce the case of a continuum part here. So given that when we train this neural network, we just use some random spec function here, it's really amazing for me to say, okay, we can just get a continuum part well under control. And also for comparison, we also share results from MEM. We just use a fitness, which means that fitness different model. What I meant is that it does not have any random structure here. So basically for MEM, it seems that there's a small bump here, but again, also within uncertainty of sVAE. So in general, this is consistent, but it seems that the sVAE outperform a little bit the MEM. So in right-hand side, that okay, I also show input as one random peak for mock data test. It's also amazing for me to say that okay, the sVAE just reproduces this one single peak structure, and for MEM there's a slight shift in the peak location here. So in this situation, that it seems that sVAE outperforms MEM a little bit. And then I go to a second. Yeah, go ahead.
So does your output give like a continuous spectral function, or does it give the parameters that are in the training set, like the C and the M and the gamma? So what is the output of the autoencoder? So the training set is parameterized in terms of these coefficients Ci, Mi, and gamma, and so on.
Yes, yes, yes.
But
yes.
the prediction from the encoder.
Oh, here, no, here input. The input have nothing to do with this training. You're talking about input and the training spec function, right?
Yeah, the input is something different. Yeah, I understand. But the output, from the autoencoder, is it a function rho as a function of omega, or is it a certain set of coefficients Ci, Mi, gamma?
Oh, I see. You're talking about here. So from encoder, this is just so basically we output mu hat, sigma hat, and pi hat. So basically just produce the probability of Z given G.
Right. Okay. And so mu hat, sigma hat, and pi hat are the
yes, just like mu, sigma, pi, and rho Z, alpha Z. Yeah.
Okay. So your output spectral function, or your prediction for the spectral function, is given by a list of numbers for sigma, mu.
Yes. Yeah. And then we have these numbers. We get P, Z, G, and Q something like this, and then we use this formula to compute everything for final spectral function. So basically, this rho bar is what we have in the model test.
Yeah.
This one. Yeah.
Okay.
Ah, shit. Yeah. So basically, the input has very less to do with training. That's what I showed in the beginning, that okay, we want to have this we have this goal in mind, that we train in the general spec function, and also output is basically got from a bunch of distributions of latent variables, and then finally transfers them into a final spec function like this.
Yeah. So let me ask it on a slightly different way. The peak on the right, you could say, well, it's almost like a single Gaussian peak. Say it's not, but yeah. So does the output of your network, after the training, after everything, does the network outputs essentially say one Gaussian with one width and one mass, or is it?
Yeah, this is just output. Here, just output. What do I mean by the output here? Yeah, this just one.
Heng-Tong, let me add something. So actually, the parameters of the Gaussians are in the hidden space. So this mu and whatever they are vectors, they are quite a huge dimensional vectors in the hidden space.
Right.
And from this, they are defining a distribution for the Z, how to sample Z from that one. So it is simply a sum of Gaussians. So it means you have a non-Gaussian distribution. You sample Z, and from Z, the decoder reconstructs you the spectral function. So it is not the Gaussian, it's the spectral function, which is reproduced finally.
Right. Okay. So yeah. Okay. Great. Thanks.
Yeah. So this is just in the hidden space. Yeah. Thank you. Okay. So let's go to the second model test. So here I want to have things more complicated. That is, have one random peak plus a continuum. So the x-axis is a width in the random peak in the input spec function. So it increases from left-hand side to right-hand side from 0.03 to 0.12. And then y-axis is the peak location of the random peak, increase from 0.1 to 0.5. And this test is with n equal 96. As you can see here, with the smallest, with the largest width in the input spec function, you can see that both MEM and sVAE, again this right line represents sVAE results, and the blue here represents results from MEM. And here we just use a general different model here that is represented by blue dots here. So you can see that in this situation, both sVAE and MEM cannot really reproduce the input spec function very well. But when you increase the width from 0.03 to 0.06, you see that reconstruction becomes better. One is that, okay, the peak head becomes closer to each other, and second, that the peak location seems to in a good ballpark. And when you increase the gamma more, you can see that the spec function can be reproduced more by both MEM and sVAE. But from here, you cannot really say that sVAE is better or MEM is better. They're just comparable with each other. And also, you can say, okay, let's fix the width and then increase the peak location. You can say that, okay, still the reconstruction quality is not that good as we expected. So in this situation just tells that the reconstruction quality depends more on the width in the input spec function rather than the peak location of the input spec function. Then we can also go to a case with a smaller number of points in tau. Sorry, because we have so many plots here. So left panel is still untitled 96, and right panel is untitled 48. You can see here in this left bottom color, you can see here for sVAE, you can still get some peak structure here, but for MEM, you don't really see a peak structure here. So it seems that everything is buried with smaller tau here. There's no structure from MEM. And when you increase width a little bit, then you will see a bump from MEM here. Certainly in this situation, it's still not a remarkable peak structure. And here, actually, the sVAE results certainly outperforms the MEM. And we increase width more, so you will see that MEM, okay, catches up and becomes comparable with sVAE, and the situation becomes more obvious when you go to the largest gamma here. So in this situation, when the n-tau becomes smaller, it seems that the sVAE outperforms MEM. Okay. So you also consider a case with n-title 48, the different lies, different uncertainties in our case. Since my time is limited, I just want to say that actually, when you decrease the noise level in the correlator, it seems that does not help that much. And then we go to mock test with non-reactive QCD. So because we found that in the previous test, if the width of a spec function is really small, then the reconstruction of spec function becomes harder. Since in the non-reactive stick QCD, the spec function you get is just like this dashed line here. It has very sharp rise in the low omega part, and then becomes flat. So actually, this is true difficulty in your reconstruction of spec functions. If you have a very sharp rise in your input spec function, it's going to be very difficult to reconstruct it. So in left-hand side plot, I show the NIQC spec function at 1.5 TC. So this blue band here represent results using n-title 48, and red band represents results with n-title 96 using sVAE. And its dashed lines will represent the results from, sorry, these dotted lines are represented by results from MEM. You can see that for the MEM, obviously that gives some fake peak structure here. It's very sharp and remarkable peak structure, and also for both 96 and 48. And for sVAE, do give some bump structure with 96 and 48, but not that dramatically. And we also show a case with a different spec function, different QC spec function input. Actually, the situation is similar. The MEM always gives a very sharp peak structure here. Then I come to my almost last few slides. I want to apply this sVAE to Lattice QCD data. So we just use our old data that is computed on quenched QCD lattice for a charmonium correlator in the pseudo-scalar channel. So we have two temperatures. One is 0.75 TC with n equal to 96, and then 1.5 TC with n equal to 48. So left-hand side shows results with n equal to 96 at 0.75 TC. So for deformed models, we're using 3 deformed models to get the results for MEM, the MEM 1 to 3. You can see the MEM results is almost independent of deformed models. And for sVAE results, that's represented by this red band here. So you can see that within the areas, the peak location roughly consistent with results from MEM. And although the peak height that's quite different from MEM here. We certainly know that from previous mock data test, the MEM sometimes reproduce input spectral function with very high height. Right-hand side, we then show the results with n equal to 48 at 1.5 TC. Again, we use 3 different deformed models. And here you can certainly say that the MEM results depends a lot on the deformed models. So there's different solid lines here. It just shifts quite a bit. And this red curve here, red curve with red band here shows the results from sVAE. It seems that this red band is consistent with the results of MEM in blue. And this blue line just shows the result obtained from the featureless deformed model. Basically, there's no peak structure in this deformed model. It seems that sVAE and this MEM1 are consistent with each other. By comparison, comparing both this plot and this plot, you see that, okay, this peak structure has decreased a lot, but to draw such a conclusion, we have to be careful on this interpretation because the left-hand side plot are obtained using n equal to 96. The right-hand side plot is using n equal to 48. A number of data points are different. So we need to compare the dependence on the n tau. So how are we going to do this? So there's a technique. Basically, we can reconstruct a collider with n equal to 96 to that with n equal to 48. But we just fix the spec function the same. We just have the spec function at 0.75 TC, but just change n tau, because this is trying to surprise the trivial temperature dependence in the kernel. So by using this technique, we can just study the spec function at 0.75 TC, but with n equal to 48. So again, we show this results similar as before. So even in this situation, this is results from sVAE. There's no peak structure, no clear peak structure from sVAE. And also from MEM, it seems that the deformable dependence is huge, because when you see this dotted green here, it just output from MEM just here, but the other one, the purple here is here, and then blue is here. So the dependence from MEM is huge. And interesting to say that again, the sVAE results is consistent with the results from MEM in blue, and this blue one just from the deformed model with a featureless deformed model continuum here. So this is the situation. Left-hand side is entitled to 96.75 TC results. Right-hand side is the temperature, same temperature but with different n tau. You see, n tau dependence is quite large. So then we put everything together. So this plot, the colored bands are results obtained from sVAE. So the black one is results from 0.75 TC, and the blue one again is 0.75 TC, but obtained with n equal to 48. And also the red one band is n equal to 48, also from sVAE. You can see clearly that this 0.75 TC and 1.5 TC just overlap with each other. So you cannot really say something on the fit of eta C here. It's really hard, because at 1.5 TC and 0.75 TC seems that this spec function is the same. So let's go to have a look at the case at MEM. So at 0.75 TC, which is n equal to 96, there's very sharp structure here. And I forgot to mention that all these results, MEM results, are obtained from a deformed model of free continuum. And then you go to the n equal to 48, at 0.75 TC. That is represented by this blue dots here. You can barely see here, but so basically that this blue dotted line are quite different from this black dotted line. And then you also go to 1.5 TC with Untitled 48. You can see everything overlap with each other from MEM and sVAE. So in this situation, we found that for Untitled 48, the sVAE results is quite consistent with MEM. And however, the other point is that it's very hard to tell the fit of eta c, sorry, at 1.5 TC. That is Untitled 48. So this comes my summary and outlook. So we propose a novel neural network, that is sVAE, and this neural network can be trained to obtain the most probable image of a spectral function. And the loss function of this neural network includes entropy and negative term, which can be balanced by a weight parameter alpha z. And when we do a training, we just train the neural network with a very general spectral function, and this noise level is mimicked to the case in Lattice QCD. And for reconstruction, we just use the last line of training and include the decoder here to get the final results. And so we have make a mock data test, 3 different types of mock data tests, and show that sVAE is comparable to MEM results and even outperform MEM in certain cases. So during the application of our neural network to Lattice QCD data, we found that sVAE is consistent with MEM results using a free continuum deformable. And the fit of eta c, again, is a table. The fit of eta c at 1.5 TC is really difficult to resolve with Untitled 48. So we're also looking forward to try our neural network with a different kernel. For instance, the QCD kernel, e to the power of minus tau omega, or for some correlators, for instance, omega squared divided by omega plus p squared. I think it's going to be interesting to see. Thank you. That's what I want to say. Thanks.
Thanks, Heng-Tong. Thanks a lot for the talk. There's a silent applause in the background. Are there any questions?
I have a first question.
Please go ahead.
Yeah, go ahead.
Yeah, on page 33, I guess. So when you augment the interval from 19.8 to 48 and 0.7 TC, 75 TC. So even though you augment the interval to a different number, the system still owns the same spectral function, right?
Yes. Yes.
So maybe you can do a mock test on this. So you know what's the ground truth spectral function. There you change the interval, trying to see what's the reconstruction performance for different interval with the same spectral function.
Yeah, that's a good idea. So in this situation, basically we actually have tried it. So since our training does not depend on any input, our training only depends on interval. So it's basically give you general situation is that with smaller interval, for instance, when you look at this guy, this plot here, with a smaller interval, the quality of reconstruction becomes much worse. If you are in the case, if you know that your ground truth has very sharp peaks, so it's going to be very hard. But if you're lucky,
okay. Sorry. So that would indicate you may draw the physical conclusions based on the large interval reconstruction.
Yes, exactly, yeah. I think large interval is really important. What make the test that with different noise level with Untitled 48. It seems that with high precision in the computational correlators does not really help that much. I think it's better just to increase the interval rather than lower down the noise level.
I see.
Yeah.
Thank you.
Yeah, thank you.
Other questions? Okay, so I have a question. So in MEM, as you showed, if you change to the default model, you kind of have an immediate diagnosis on whether it's default model dependence or not. So very quick conclusion you can draw. So in the auto-encoder, is there a similar thing you can change in the algorithm that you can, change and look for robustness?
That's a very good question.
So the number of layers, the size of the latent space.
Actually, that's also one of the questions that asked by referee.
It's not me, I can tell you.
Okay, so the thing is that probably can improve our quality of the results is that we do a training spectral function. For instance, here we can increase the number of M here to make to make a resolution in omega space much more. In this situation, probably can probe higher precision in the even resolve the sharp peaks. Because here, for instance, we fix the training parameter MI in the range of 0.05 to 0.8, and we only use 50 number of Gaussian peaks. So that means that our resolution in the omega space is 0.8 divided by 50. So maybe increasing this number can help us to resolve the peak, resolve sharp peaks.
Yeah, this is like a size, essentially a size of a basis, except that it's not really a basis and they're not orthogonal, but it's yeah. The number of Gaussians is just a choice you made to parameterize.
Yes, yeah, for training. But this is all based on the Gaussian mixing model. So
I know machine learning people use fancy words for trivial things, isn't it?
Yeah.
And yeah,
also have fancy words for trivial things.
Yeah, so it's kind of just following up on that question. So I guess the thing is, the default model in the MEM is sort of putting in a strong bias, and here it's any bias that you're putting in is from the training set, and I guess what you're trying to do is putting in, I guess, as unbiased a training set as you can by having a large range of training functions. So the question is, so as opposed to if you just put in a few Gaussians, then all you're going to get is a few Gaussians. So the question is, would this way of doing it actually? So it's interesting to see that your results are looking similar to the MEM, sort of most similar to the MEM with basically a featureless default model. So it's a question whether you're kind of by just this big average, big set of undifferentiated training, a big undifferentiated training set where you're in some sense biasing it towards a featureless function, or by this yeah, so I guess that's my question.
Yeah, I understand. Yeah,
observation.
So yeah, that's a very good question. So actually, we also don't really know why our results tends to be consistent with MEM with a fictionless default model. But actually, in our training, we don't really base a different spectral. What we do is just we use this as true pair in our case. So so here in the MEM, you have this default model, right? Anyhow, you have tune this default model, just check the default model dependencies. But in our sVAE, we train it, and we train the neural network, and in the same time, we know the answer, right? We know the answer and put it in this ground truth value of a spectral function into an entropy term. And then somehow this neural network is meant to balance the prior information and the likelihood function.
But the ground truth here, the ground truth here has the assumption though that your training data set, so the ground truths G and rho, come from an ensemble, of training data, which is biased by your choice of
Yes. But here, as Junua said, I'm not really sure we're using such kind of course, this is just a bunch of Gaussians, right? They have a lot of structures here. I'm not really sure why and how to say that this is a bias towards to a fishness spectrum.
No, I agree. This
it's amazing. So actually, I don't know. So that's your answer to
I guess it's a question just of the averaging out of all these different things. If you don't have, that's sort of, so then especially if it then results in one, if all these training sets, I mean, just results in one ground truth spectral function at the end, then you're then just looking at this. Okay, the average of this is something relatively featureless.
Yeah, that's actually a good idea. We can just check. We can check our training sample, right? Whether to do a stochastic average of these training samples to see whether, okay, the average is just a fishness one. Yeah, we can have a look at it. Yeah, that's a good, interesting point. Thank you.
Okay, any more questions?
May I have a technical question again? So
yeah, sure, go ahead. Yeah.
So for different noise levels, do you do different training?
Yeah, I'll do different trainings. Yes. Yeah.
So what
training
if you, so what if you provide the stochastic correlator G from different noise levels inside one training? So what will happen?
Actually, we didn't try that, but we consider that will be inconsistent, right? So if you train your neural network with a very precise data, but then you use that neural network to construct a correlator which is very noisy, I think that can be inconsistent.
That's noisy, but with different noise levels. I mean, you have different data points. Each data points are owing different noise. So
yeah, that's also a way how we do a training, right? That's actually a very interesting question. So when we train a neural network, we're trying to mimic the case in the Lattice data, because we know in the Lattice data the correlators themselves are correlated in distance. So in this situation, we just use this sigma equal to b tau times this correlator. So in this we just use the noise level from Lattice data. Of course, that this is a simple ansatz to mimic the noise level in the real data. To make it more complicated, it might reveal something new, but I don't know. Yeah, that's a good point. And again, the one missing point in our study is that we haven't looked into a case for instance, we showed likelihood function. We're just looking at the diagonal one. So next step, we're also going to look into a case including the covariance matrix. That's straightforward to do, and we're currently working on it. Yeah.
Thank you. Yeah,
thank you.
Okay, I see no more questions. So thanks a lot, Heng-Tong. It was good to see you.
Yeah, thank you a lot.
Thanks for the talk. Yeah.